Hello everyone, today we are going to talk about minerals. So what are minerals? Minerals are the ingredients that make up rocks, which make up the Earth's surface, aka geology. In order to have a better understanding of rocks and rock formations, we need to understand the minerals that make them up. Minerals are naturally occurring, so if you can imagine a trail in the woods with a stream. We got some water, and then we've got some trail right next to it, and we got some rocks on the trail. All minerals are naturally occurring. That means you can find them in nature. So these would be like little rocks that you might see on the side of the trail. Some minerals are harder to find than others, and they require specialized equipment to extract teeny tiny amounts. Others are so common that they're just laying around. An example of minerals that are laying on the ground would be hail. So this picture isn't going to be the greatest on the screen, but you can see that there's pictures of hail on the ground. Hail meets the definition of a mineral because it is naturally occurring. Minerals are also inorganic. I brought in a couple of examples of things that could be minerals. So this is an example of a sapphire ring. This ring is actually not naturally occurring. This sapphire was created in a lab. I did not realize that when I purchased the ring. It ended up, I tried to exchange it for a better ring, and they sold it to me for full price, but wouldn't buy it back for full price. So that was kind of fun. I'm trying to get this to focus, and it's not really working. However, on the side, there are some diamonds, and those diamonds are naturally occurring. Both diamonds and sapphires are inorganic. I also have an example of some garnets. So these two are garnets. They look very similar to rubies. Fun fact, rubies and sapphires are the same material. Got some emeralds, and I think this is topaz. So just some examples of some naturally occurring inorganic materials. I also have this, which is not naturally occurring. This is not a gemstone, it's a piece of plastic. And I bought this when I was a kid, so like obviously doesn't have any value, but just it's a pretty looking ring, and so I bought it. I didn't know that it had no value until I was older. So those would be examples of minerals that are both naturally occurring and non-naturally occurring, and then inorganic. So examples of things that are not organic would be a pearl necklace. So that comes from a living thing, so that makes it organic. And then, like I said, the naturally occurring, the lab-created sapphire would also not be. Minerals are also solid. The jewels that I showed you before, the gemstones, those are minerals, they're solid. So examples of things that would not be solid would be, I'm just going to draw a picture of this. So mercury is a metal, but it is so thermometer. So let's say this thermometer is mercury. Is not a solid, it's liquid. So that makes it not a mineral. So a lot of metals are minerals. However, mercury at room temperature is a liquid, so it would not be a mineral. Minerals are also, they have a crystalline structure. Crystalline structure. You might remember learning about geometric shapes in your junior high or high school math classes. Crystalline structures are close enough to the same thing for this example. Minerals have to have a crystalline structure that we can observe. So another rock example that I have is obsidian. So I've got two samples of obsidian. This is just a classic obsidian example from a rock sample, but I have an obsidian necklace. Now I got this obsidian necklace in Costa Rica. I was observing Mount Arenal in Costa Rica, And they shaped the obsidian. So this same rock is in a circle. You just put the rock, you chip it away, and then put it into a tumbler, and it makes a circle shape. Obsidian does not have a crystal structure, so that means it cannot be a mineral. So that's an example of something that's not a mineral. But if you look at something like, so this wooden block is just an example of a shape. This is a crystal that happens to have, you know, a crystal shape. It's a very well-defined crystal shape. So that would be an example of a mineral. And then the last thing, so minerals, they have to have 5 things to make them a mineral. They have to have a definite chemical composition. How do you know if it has a definite chemical composition? This is an example of the periodic table, just an estimate of the periodic table. So far, we've talked about ice. So ice is made out of hydrogen and oxygen. Oh, I forgot these guys. The chemical composition of water is 2 hydrogens and 1 oxygen, H2O. We've also talked about the lab-created sapphire ring. So real sapphires are the mineral corundum, which is aluminum oxide. So aluminum is right here. Aluminum and oxygen mixed together. We also talked about diamonds. So diamonds in their pure form are just carbon. I talked about mercury. Mercury forms a mineral called cinnabar. So when mercury and sulfur, so mercury is way down here, it's heavy metal, very toxic, good stuff. And sulfur, right under oxygen. So mercury and sulfur, when they combine, we get cinnabar, and it is a solid. When it chemically combines with other elements, it does form a solid. We talked about calcite, was that funny looking rhombohedron. That calcite is, we've got some calcium, which is over here, about right there, and it's made of carbon and oxygen. So that would be, those are all, so if it is composed of things that can be found on the periodic table, it's an easy way to know if it is a mineral or not. In order to understand the chemical composition of minerals, we do need to look into the periodic table of elements. So what are elements? An element is a group of atoms with the same number of protons and the same chemical and physical properties. So here we have hydrogen and carbon. All hydrogen atoms have 1 proton. They are gases at room temperature, and they're very, very reactive. So we very rarely find hydrogen alone in nature. On the other hand, carbon is made of 6 protons. It's a solid at room temperature, and it's not very reactive, which is why we can find it in the form of diamond or graphite, just hanging out on its own. So what are protons? Proton is a positively charged particle, and they're the defining characteristic of an element. Neutrons make up the rest of the mass of an atom. Neutrons were initially hard to detect because they are neutral, so there was no charged particles that we could send through them to try to measure their presence. But they knew that something was there because they weigh the same as protons, so they weigh a lot, and so we knew that there was something there. Isotopes are what happens when we have different numbers of neutrons. So right here we have 6 neutrons with these 6 protons. We call that carbon 12. If we were to add another neutron, we would have, so we have 6 plus 6. If we added another neutron, we would have carbon 13. So it would have 6 protons plus 7 neutrons. That is how we get isotopes. Isotopes are what we use to determine the age of rocks, and we will talk about that more in depth in the geologic time scale chapter. Finally, to have a totally neutral atom, so if we have all these protons with a positive charge, in order to have a neutral atom, we need to have something that's negatively charged, and those are electrons. Electrons exist in this space around the atom. They're teeny tiny. They have almost no mass, that they are responsible for all of the bonding with an atom. Atoms really, really like to have 8 outer electrons. We call those valence electrons. And this affinity that atoms have for 8 outer electrons, we call that the octet rule. Here we have mercury, and it has 2 electrons in its outermost ring. And I talked about mercury being a component of the cinnabar mineral earlier. It has a total of 80 electrons, but it only has 2 in its outermost shell. So these are the valence electrons. Those are the ones that bond with sulfur. So when it gets, but because it only wants 8 in its outermost shell, it's actually going to get rid of those. In the action of getting rid of the 2 electrons, mercury, when it gives up those 2 electrons, it will become positive. So we get rid of these 2 electrons to get our 8 valence electrons, our happy atom, but now we're 2 electrons short, so we end up with a 2+ charge. So Hg 2+, mercury with 2+ charge. Sulfur, what is how cinnabar is made. Sulfur, on the other hand, has 6 valence electrons. It really wants 2 more. So we want 2 more electrons. Sulfur has 16 protons, and now it's going to have 18 electrons, and it's going to have a 2 negative charge. So it takes the 2 electrons from mercury and gets a -2 charge, but then this negative and this positive, that is what causes that bond. It has this ionic attraction. In our periodic table, we have, you're not going to see this necessarily from, unless you look at periodic table, there's a stair step here. These are our nonmetals. These are our metals. Lots of metals on the periodic table. An easy way to remember if a compound is ionic is if you have a metal plus a nonmetal. Those are ionic. If we have 2 metals together, or 2 nonmetals together, we call those covalent bonds. And I'll explain covalent bonds in a little bit. And then if we have 2 metals together, we call those metallic bonds. And I'm going to write the word, because I don't have that on there. So metallic bonds are formed from 2 metals, or even just a metal by itself. Ionic bonds are formed from metals and nonmetals combining. And covalent bonds are formed from 2 nonmetals combining. Covalent bonds, let's do carbon, 6 electrons are on the outside. Carbon only has 4. Let's do oxygen. Has 6 are on the outside. So it is too short. If we put another oxygen molecule right next to it, which is also too short, they can form a bond between 2 of the electrons. So then we have 1, 2, 3, 4, 5, 6, 7, 8. This also shares those electrons. 1, 2, 3, 4, 5, 6, 7, 8. That is called a double bond. It is also sharing electrons. Like I said with metallic bonds, that is metals just hanging out. So let's do gold. Gold, it has a 3+ charge. But sometimes it just hangs out with other gold. It doesn't actually need a charge. So let's just say it has those 3 extra electrons, 1, 2, 3, 1, 2, 3, 1, 2, 3, and they're just kind of hanging out. All those electrons are just hanging out, which creates negative charge. All that negative charge builds up and gives us things like electrical conductivity. So what does all of this talk about electrons have to do with minerals? Well, the ability to conduct electricity is just one special property that allows us to identify a metallic mineral from a non-metallic mineral. For example, if I have a piece of hornblende, which looks like this, and I have a piece of hematite or magnetite that looks like this, you might not be able to necessarily tell them apart from each other because they both look like black minerals. They're both pretty jagged. But if I were to connect them up to an electrical wire or a flashlight, I could see this is going to conduct electricity and this one is not. If the ability to conduct electricity is a testable property of minerals, what are some other properties? Ambiguous properties are shared by multiple minerals, which means they cannot be used individually. For example, quartz, halite, and calcite have clear color and are transparent. So if I were to try to identify from just the clear color and their transparency, that's not going to be able to help me to distinguish between the three minerals. Luster is a mineral's ability to reflect light. We have two types of luster, non-metallic and metallic. Metallic is pretty easy to see. It looks like a hunk of metal. It's very, very shiny. It looks metallic. Non-metallic, on the other hand, it does not look like a piece of metal. Most of the minerals on Earth are non-metallic. We have a lot of ways to classify non-metallic. As I said before, we have some different metallic types. So this would be an example of quartz. It has that vitreous or glassy appearance to it. Calcite is another one that has that kind of glassy, almost see-through appearance. They don't always have to be see-through. This would be an example of fluorite that is glassy. It looks like shatters of glass. Another one is dull or earthy. This is an example of bauxite. It is a very, very earthy and dull mineral. Bauxite, fun fact about bauxite, it is the ore for aluminum. Aluminum is the one mineral that it is cheaper to recycle it than it is to dig it up. Well, and you saw how orange it was. It's very, very difficult to process it, so it's much cheaper to just recycle. Probably my most pearly one. It's a little bit vitreous, but it's just very soft and smooth and very shiny and pearly. This is my fibrous. This is in that. I don't have it on here, but this is very fibrous. You can see there's lines cutting through it. It does actually feel very silky. You can't really tell that. Last but not least, one of my favorite minerals. This is graphite. It feels greasy. That is because it's rubbing off in my hands. And graphite, standard test, you can use it as a pencil. These are all lusters, which are a diagnostic property, and these are non-metallic lusters. Another diagnostic tool that we have is streak. So if color is ambiguous, and we can't use that to diagnose which mineral we're looking at, streak is the diagnostic version of that. It is the color of the powder. Now, I'm going to specifically use hornblende as an example. So I've got the streak plate. It is mostly clean. And then I've got this mineral that looks black. Hornblende looks black. When I use this on the streak plate, it has almost, you can't really tell on camera, but it's like a light gray. So it's a very, very light gray color. So that's an example of why color is ambiguous, but streak is actually defining. Here's another one that has gold color. Many of you are going to know that this is not gold, just simply because I would not be working here if I had this much gold. But you can tell that it's not gold because it has sharp edges. Gold is blobby. Also, most of you are familiar with fool's gold, so this is fool's gold. It's called pyrite. But when I put it on the streak plate, it's kind of a dark. Again, my video is not picking this up very well, but it is dark. It is a dark greenish gray. So it doesn't match the color. This is another one. This one actually does match. So we've got, this is galena, it's kind of a bluish gray color. When I put it on the streak, it's bluish gray. Hardness is another diagnostic tool. Definition of hardness is the resistance to scratching. So the way that we measure hardness is by scratching it against other things. We use other things to measure that. So the example that I already used today is graphite. So your skin, the hardness of your fingerprints is hard enough to scratch off graphite. So that means graphite is an incredibly soft mineral. So it's going to have a hardness of 1. So this is going to be very difficult to see. I apologize, this camera is just not zooming in. But I'm going to just take my fingernail and yeah, I cannot scratch it. So, oh wait, right there I got some. I do have gypsum. That should be scratched with my fingernail. Yeah, that I can scratch with my fingernail. I do have talc, but the talc that I have has asbestos in it. This is saying a penny will scratch calcite. I don't know if you guys realized, but the penny got demoted recently. That's kind of interesting. Okay, so I'm going to take this penny and I'm just going to go scratch it, and yeah, it gouges out the calcite. So penny is tougher than calcite. I don't have any wire nails, but I do have my streak plate. The streak plate has a hardness of 7. It's made of quartz. So if I were to take my diamond ring or my sapphire ring, both of those would scratch the streak plate. So fluorite with my copper penny. Fluorite is harder than a penny. It should scratch the penny. And yep, there's a nice big gouge in the penny. Earlier, I showed you both quartz and calcite. The crystal shape is significantly different. That would be how I would diagnose between the two, but I also have galena. So this, if I had galena and graphite, that might be a way that I distinguish between those two. We have these hard edges. Any crystal shape, that can sometimes be a diagnostic tool. This is one sample of quartz. This is another sample of quartz. This is not as easy to see the crystal shape. One sample of calcite, another sample of calcite. Calcite is very distinguishable. It is one of the few minerals that you can look at and tell right away that it's calcite. Another one that we have is chlorite. So from this, you can't really tell its crystal shape, but here's another sample that it grows in these perfect octahedrons. Crystal shape is a property that dictates cleavage, which is exactly what it sounds like. You can think of it as plumber's crack or a busty woman in a tank top. When the mineral breaks, it's a nice clean pattern. This happens because the individual chemical bonds are weak along a section and it creates a clean break. An example of perfect cleavage would be something like mica. This breaks along into these little sheets, and I don't want to tear up this sample, so I'm just showing you a little bit, but it breaks off into these perfect little sheets. Now my fun fact about mica is that when this is ground up, this is the mineral that is used in makeup to make it sparkly. It does not need to be a perfect straight line. It can be cubes. So this is galena. I've shown this to you a couple of times. When galena breaks, it breaks into perfect little cubes. I'm trying to find my little samples. So these are very difficult to see. Oops. And they just break off into little perfect cubes. Tenacity is a mineral's resistance to deformation. An example of something with high tenacity is going to be something that is elastic or ductile or malleable. So if you think about metals, those are all traits of metals. Some examples of copper. So obviously we have a copper penny. The copper was pounded flat like this, pounded flat and then wrapped around the zinc. So that is how, actually that's probably not how they're made, but you can think of it that way. It's just a thin piece of copper wrapped around the penny. That is malleability, being able to be hammered flat. Also, being able to bend and not break. That is a property that's common in metals. We have these samples of galena that were hammered and it was broken. So that would be brittle. The fracture is what happens when all of the bonds have equal strength and weakness, and when it breaks, it creates all sorts of different types of surfaces. So back to our fluorite, we see that there's actually pretty decent. So this would be breaking off into cleavage. It has those shapes. But when we look at quartz, there's no defined shape where if I broke this, it would just shatter. Actually, yeah, if I broke this, it's going to break off into tons of little pieces, but it's going to have cleavage. It's going to have those nice, clean lines. But those would be examples of the difference between cleavage, fracture, tenacity, and crystal shape. Or there are some special properties of minerals that make them identifiable with just a single test. Other properties include density. Earlier I showed you samples of hornblende and magnetite. If I were to pick these up, hornblende is much lighter. Like, I can just tell that there's more heft to the magnetite. So that tells me that this is a denser material. Density is a unique property. It is a diagnostic tool. It tells you what the chemical structure is. Obviously, magnetite has iron in it, and hornblende is made of mostly silicon and oxygen, so that's going to make it much lighter. Smell is another one. So both pyrite and galena, I've showed both of them to you, fool's gold and galena, they both have sulfur in them. They're made of sulfur. So pyrite, I forget what pyrite is made of. Zinc sulfide, and lead sulfide. So this is made of zinc, but if I scratch the surface and smell it, it smells like rotten eggs. Same with this, scratch the surface, smell it, smells like rotten eggs. Both of these have sulfur in them. Lead sulfide, the pretty blue color that you see, that's from the lead. Yes, I'm handling lead. I think it's just part of the job. I've got just a magnet here. I got a piece of magnetite. Pretty easy test. That hornblende that I had earlier, not magnet. The galena, not magnet. Pyrite, not magnetic. This is hematite, so this is magnetite. It's actually magnetic. This is hematite. It's made of iron. It's just not magnetic. And then double refraction. I wrote this really big so that you can see this hopefully on camera. So you can see a little bit on the camera. The words are, I'm going to see if I can get this to zoom in at all. There. You can see how the letters are kind of double. That's called double refraction. So this is calcite. That is one of those properties. We do have a mineral, I forget what it is, but it looks just like calcite. It has the same shape, crystal shape. Plop it over the words and it doesn't have that double refraction. That's how you can tell whether it's calcite or not.
So I know I get really excited about minerals. I do geek out a lot. So we're going to talk about how minerals are categorized, and then we will be done. Minerals are categorized in many ways. First, there's the economic value. I already showed you a bunch of jewelry that I have that were used for minerals. So that's one of the obvious ways that they have economic value, but they're also used in manufacturing. So, for example, we use graphite for pencils, but graphite's #1 use is actually in brick making. So anything that doesn't necessarily have an economic value, we call that rock forming. And those are going to make up the most abundant elements on the Earth's crust. We also categorize minerals into silicates and non-silicates. Silicates are the most abundant minerals on Earth. In fact, the continental crust is primarily made of silicates. They are much less dense than metallic minerals that make up the ocean floor. So this accounts for the lighter colors of the continental crust and the darker colors of the oceanic crust. It also accounts for why the continental crust kind of floats on top of the oceanic crust. Feldspars are the most common. An example of feldspar. So this looks, it's the same color as my skin, so it's kind of a rosy pink color. And that's the most common mineral on the continental crust. It is used to make strong glass like toilets. So it's used for like making porcelain toilets. So because there's so many silicates, we actually classify them into light and dark. And remember how I said color is the least diagnostic tool? We're not talking necessarily the overall color. We're just talking light versus dark. So if I have these two minerals, and this one's light and this one's dark, I can pile them into two separate piles, and I'm going to have probably equal amounts of light, equal amounts of dark, and then I'm going to have a bunch of metallics. So for our non-silicates, we have oxides. All right, so our non-silicates we can break into a ton of different categories. So magnetite, we've already seen the magnet's still attached. That's iron oxide. So that would be an example of an iron oxide. I don't have any phosphates with me. Sulfates, an example would be gypsum. So there's my gypsum. I got sulfides. I've shown you both pyrite and galena. Those are both sulfides. I've already shown you calcite, a couple of different versions of calcite. Fluorite, I've shown you that one, that's a halide. And then the native elements is my little copper sample. Because we can find copper ore. I wonder if I have I have a better one. This is actually really cool. This is a straight sulfur ore. So these are sulfur crystals. And this was collected at over by Yellowstone. So those sulfur crystals. I just smelled it. It does smell like rotten eggs. Native elements are anything that you can find in nature. So like the gold nuggets that people found in the 1800s in the Black Hills in San Francisco. And I think there was a pretty big gold rush up in Alaska. Also the diamonds that we have in Arkansas. Anything that's just laying around like this, those are native elements. This has been processed. So why is it so important to understand minerals and chemistry? Minerals make up rocks, which makes up the solid earth and all the landforms that we see. People need to understand which geologic formations are appropriate for building houses on, growing food, or raising livestock. And because we're an energy-dependent species, we also need to know where to find the minerals that support our energy infrastructure. Like chalcopyrite is a ore of copper for wires, or coal for electricity. So we need to know, and coal is not a mineral, it's a rock. But we need to know where to find these things. And that is why it's so important to understand minerals and the chemistry that makes up the minerals so that we can understand the rocks and then the land formations that make up the rocks.